So on Monday, we first looked at some chemical reactions and what happens when we are looking at a chemical reaction from a statistics perspective. Okay, we found the relationships between the chemical potentials, and in fact, we had seen that in equilibrium, the densities should be fixed. The ratio of a function of the densities should be fixed and depend only on the temperature. This is something that should be familiar from Chemistry 1, first year undergraduate course. Then we started the so-called bosonic systems. Let's assume we have a non-interacting system of bosons, an ideal gas basically, the system that we had studied over and over again since the beginning. But this time we will be looking at what happens at low temperatures. If you remember when we looked at the classical ideal gas, in the ideal gas in the classical limit, we found the entropy, but it violates the thermodynamic laws. Entropy doesn't go to zero at zero temperature. In fact, it diverges. So something should be happening. And in fact, what we see is at low temperatures, quantum mechanical effects can no longer be ignored. So we have to take into account the quantum mechanical effects. And those effects basically solve the discrepancy between the ideal gas and the thermodynamic laws. And so basically, these are the three equations we have. Whatever system we will study, we should solve Z from n is equal to that sum over single particle states. By the way, these sum over single particle states, we can also write them as an integral over energies with the given density of states. And in fact, that is what we had done also before. But before looking at the details of what is actually going on in this system, we wanted to get an idea of what happens, how does the chemical potential change with temperature. So first of all, if we want this distribution over here to be finite for all energies, we had seen that chemical potential has to be negative, has to be less than all the energies. And since we are fixing the ground state energy to zero, so the chemical potential has to be negative, then we looked at how the chemical potential should change if we are changing the temperature. And we had seen that the Z, the fugacity, or similarly the chemical potential should decrease if we increase temperature. And in fact, it should look like something like this graph over here. Now, if we have such a graph, the question is what happens if we lower the temperature even further? Well, it might go to zero, chemical potential, or it might not go to zero. So these are the two. It cannot cross, it cannot become positive, that is definite. It has to be negative, or zero at most. But does it become zero at a finite temperature? That's a question that we still have to address. And okay, this is here we had the mathematical treatment just using this equation. If you take the derivative with respect to t at constant n and v, that gives you how the z should change as a function of temperature. And it tells us that it has to be negative. But we can also come up with a more physically intuitive answer just looking at how this Bose-Einstein distribution behaves as a function of temperature and chemical potential. You see, if you take this function as a pure mathematical object, lowering the temperature basically means increasing beta. If you don't change mu, but just increase the beta, the exponent becomes larger. And if the exponent becomes larger, the value of the Bose-Einstein condensation basically drops. So that black curve becomes the red curve if we don't change the chemical potential. But we know that we have to fix this constant. You see, if you don't change the chemical potential, but lower the t or increase beta in that sum, all those terms become smaller. So if a number of terms, when you sum them up, gives you a number, if you change all those terms with smaller numbers, well, the sum will be smaller. So we have to do something else to keep the number fixed. And well, again, this plot tells me what I should do to increase the sum. The sum is basically the area below that curve for epsilon from 0 to infinity. So if you would like to increase that area, I have to move mu closer to 0. so that the point where the distribution diverges approaches 0, and hence at smaller energy values the distribution becomes larger, whereas at larger energy values it will still become smaller. Again, this treatment also, this treatment tells us two things basically. At low temperatures, more and more particles occupy the zero energy state. And chemical potential has to increase as you lower the temperature, which was a result we had obtained also just taking the derivatives before. Now, in fact, one of your friends was asking a question, what happens if we do take the limit as t goes to 0? Well, you see, if you look at this function, 1 over e to the power beta epsilon minus mu minus 1. If you take the limit as t goes to 0, well, let me write it slightly differently. Beta just diverges, so e to the power beta epsilon becomes infinite. Of course, if epsilon is not 0. So this just becomes 0 if epsilon is not equal to 0, and 1 over z0 minus 1 minus 1 if epsilon is equal to 0. Z0 is the fugacity at 0 temperature. And basically this number is nothing but n. So we see that this distribution already tells us that all the particles basically go to the ground state. Well, that number is not n, sorry. Yeah, that number is n. So all particles are now in the ground state at t equal to 0. And then we said, okay, so here we have all this argument is basically how do we derive the density of states for a free gas. And then, okay, this is n expressed in terms of the density of states. N0 is the number of particles in the ground state. And you see, N0 is just 1 over Z inverse minus 1. Whatever Z is. At all temperatures, this is what N0 is, just the Bose-Einstein distribution for epsilon is equal to 0. Now, if we have two cases, Z can be very close to 1. That is the case when chemical potential is very close to 0. In that case, N0 can be large. If Z is very close to 1, Z inverse is also very close to 1. So it's almost 1 over 0, which is infinite. Z cannot be exactly equal to 1, but can be very close. So unless Z is very close to 1, N0 is negligible. The first term is proportional to V, the volume, which in the thermodynamic limit basically diverges. So the N0 is negligible unless Z is very close to 1. And then for
we have the expression for the total number of particles, where N0 is the stuff that's in the ground state.
Yes.
So everything else is an excited state. Should the integral still run from 0 to infinity then?
what is the contribution of x is equal to 0 to that integral? Well, you see there's a square root of x. When x is equal to 0, it's just 0. So there's no contribution from the point x is equal to 0 to that integral. So I don't really care whether the sum starts from 0 or 0 plus.
Right.
A number very close to 0.
And at critical temperature below, we just have N0 there. That's this.
No.
No.
We will see what happens below the critical temperature. You see, on Monday what we did was what happens in the classical limit. Now we will ask ourselves the question on the other limit. What happens at low temperatures? And eventually look at what happens at 0 temperature limit. That is what we will do today. But this is the general expression. And in fact, we define this so-called weird function, so this is what we have. We have to solve this equation for Z. Then we looked at the limits when Z is not equal to 0, Z is not close to 1. Well, if z is not close to 1, n0 is negligible because of our previous arguments. If we neglect n0 and z is not equal to 1 or close to 1, now z, again, keep in mind that it's smaller than 1, so it's a number smaller than 1, somewhat close to 0. Well, in that limit, we have this equation to solve. We have determined what this g function is. It has such an expansion for an arbitrary nu. So this is our condition. You see, we are looking, this is the expansion valid, not necessarily in the large temperature limit. We don't know that yet. But this is the limit when z is very close to 0. But if z is close to 0, you see this n lambda is h bar over 2 pi m kt to the power 1/2. So if n is fixed, you have a fixed number of particles in a fixed volume, then the only way that z can change is the temperature. So z, which is almost equal to n lambda cubed, can be very small, close to 0, only at t becomes very large. So that is why we know that z close to 0 limit is actually the large temperature limit. Although I titled this section high temperature limit, I don't really yet know what z is equal to 0 limit, z close to 0 limit means, but this tells me that it is the large temperature limit, keeping the number and volume fixed. You see, I can also write this n lambda cubed as lambda cubed over v, volume per particle. You see, v, small v, is capital V over n. That is the volume per particle on one hand. On the other hand, I have this particle which has some thermal momentum, and corresponding to the thermal momentum, it has a wavelength which basically characterizes its quantum mechanical effects. So lambda cube is essentially the volume of my particle. Volume of the wave of my particle, let's say. So if n lambda cubed is very small, basically means that lambda cubed should be much smaller than small v, the volume per particle. So the volume of the wave of my particle should be much smaller than the volume per particle. That is, the wavelength of my particle should not extend to the other particles. It should be very localized. So that is essentially the quantum mechanical limit, the classical limit we are talking about. So the particles, they do have the quantum mechanical wave properties, but if they are localized, and if they don't come close to each other, well, they don't feel the quantum mechanical properties of each other. So that is why also this is the classical limit. Now today we will look at what happens as they approach together somehow. Not necessarily overlapping, that we will also study, but let's say that they are not really they are not purely classical, but the volume per particle is somewhat becomes comparable to lambda cube, the volume of the wave itself. Then we expect to see deviations from the classical behavior. So let's try to find out what those variations are. The first correction. That is the first thing we will do today. And then we will look at what happens at the other limit when z approaches 1. So any questions up to here? You see, the first thing I need to solve is this equation. But now keeping the corrections. So G G3 over 2 Z is just Z plus Z squared divided by 2 to the power 3 halves. This is what we had derived. Plus of the order of Z cube terms. Now Z, we already know that at the 0th order approximation, this is n lambda cubed. Let me find the correction to this one. I'm already looking at the limit when n lambda is small, but not very, very small, just very small. So I would like to keep the first correction. Now this delta is just a number I would like to determine. I'm expanding z as a, you see, this expression already tells me that z is a function of n lambda cubed. It's not a function of n or v or t independently. It is a function of only that combination. So I'm just making a Taylor expansion of z, and I already know what the first term is. First term is n lambda cube. I have to determine delta using that equation. So n lambda cube should be equal to n lambda cube plus delta n lambda cube squared plus n lambda cubed plus delta n lambda cubed squared plus the other terms squared divided by 2 to the power 3 halves. And all those dots just basically represent terms of the order of n lambda cubed cube. Well, this is n lambda cubed plus n lambda cubed squared. There's this term of the order of n lambda cubed squared. There is also the contribution from this term, which is plus 1 over 2 to the power 3 halves, plus there are other terms of the order of n lambda cubed cube, which I ignore. So for this equation to be satisfied, delta should be equal to minus 1 over 2 to the power 3 halves. So I know what delta is, in that which is the second term in the expansion of z in n lambda cube. Well, the rest is basically I have to put these in other expressions. You see here, I calculated what PV over KT is. Or P over KT is 1 over lambda cubed. Well, you see this expression over here is valid at all temperatures at all Z. Whether as long as I have a non-interacting bosonic gas, that is my pressure, temperature, and the other parameters, how they are related. So G5 over 2Z, I already know what that is. That is Z plus Z squared divided by 2 to the power 5 over 2 plus other terms. But I already know what Z is. So this is 1 over lambda cube. N lambda cubed is the first term. Minus 1 over 2 to the power 3 halves n lambda cubed squared. These two are from the first Z. Now I need to take the square of Z, which will be plus n lambda cubed squared divided by 2 to the power 5 over 2 plus other terms which are of the order of n lambda cubed cube. This is pressure over KT. Which will be, well, let me take n lambda cube out. This will be n over V. You see, n lambda, small n is capital N over V. Then I have 1 plus or minus 1 over 2 to the power 5 over 2 n lambda cubed squared plus higher order terms. Well, this is how the pressure changes as I change for a fixed N and V. If I lower the temperature, I will start seeing, eventually I will start seeing deviations from the classical law, and this will be the first correction to the classical law. The first term is the classical limit. And this is the first correction.
Didn't we take the n lambda cube out? Or is it still the square?
Thank you. Any other questions? So let me collect the basic equations I have. P over KT will be 1 over lambda cubed G5 over 2Z. And lambda cubed is equal to G3 over 2Z. You see, these are valid, whatever the temperature is. U, the energy, we had also shown that this was 3 over 2 PV, which was 3 over 2 KT, well, if you like, 3 over 2 KTV, 1 over lambda cubed G5 over 2Z. This is U. Well, here there's a plus N0. Now basically the rest is just playing with these three equations. Now let's look at the other limit. Z is very close to 1. Well, let's look at what G nu is. Okay, so this is almost G nu of at Z is equal to 1, which, if you like, n to the power, now, n from 1 to infinity, 1 over n to the power nu. Does anybody recognize this function? So as far as I know, you are dominated by theoreticians. Haven't you heard of how come the sum of positive integers equal to minus 1 over 12? This is the Riemann zeta function. The relation with the sum of integers being equal to minus 1 over 12 is this one. Well, this is one definition of the Riemann zeta function valid for nu positive nu. Nu larger than 1. As long as nu is larger than 1, it is finite, it is defined for all nu. But there are other definitions of the Riemann zeta function, and those other definitions, which are valid for any value of nu, tells us that the Riemann zeta function evaluated at minus 1 is 1 over 12. So, well, that basically simplifies our treatment significantly. You see, on one hand, we have n lambda cubed should be equal to this is the equation I'm looking at. Plus n0. Well, I know what n0 is, the number of particles in the ground state. Well, in fact, since I know Z, I don't even need to solve for this equation. What else do I have? Well, let's look at at what temperature does N0 appear? You see, this tells me that as I lower and lower the temperature, lambda becomes larger and larger. So the first term becomes larger and larger. So N0 is a positive number. Well, the critical value this is equal to 0. So NH bar cubed divided by 2 pi mkt raised to the power 3/2. This is the critical temperature, minus equal to zeta 3/2, or T critical is equal to NH bar cubed divided by zeta 3/2 to the power 2/3, 1/2 pi mk. Well, whatever that is. I just solved this equation. Take the 2/3 power of both sides, solve for. Okay. You say this is larger than 0 if zeta 3/2 is finite. Let's say that you don't know the zeta function. And remember, although here I just used this zeta function over here, remember the definition of G3/2z. This is 1/gamma nu, 0 to infinity, dx x to the power nu minus 1 divided by, I'm looking at what happens at z is equal to 1 divided by e to power x minus 1. And this is so is this integral finite? How can you show that this integral is finite? You see, in this simple case where we have a three-dimensional Bose gas, this is the integral we obtain. Nu is 3/2, so this is 1/2. If you trap it on a plane or on a line, this integral might not be finite. So how can we show that this integral is finite? Because if this integral diverges, the critical temperature is 0, which basically means that chemical potentials become 0 only at absolute 0. And hence there is no phase transition. There is no Bose-Einstein condensation. So why does any integral diverge? Not necessarily this one. What might be the reasons for the divergence of any integral?
Function might be going to infinity.
Well, the integrand might diverge. That's one reason why an integral diverges. A second reason for the divergence is that the range might be infinite. So even if the function is finite, if you are integrating it over an infinite range, you see it's basically an area whose one length is infinite. Well, if you the area might still turn out to be infinite, even if the function is finite everywhere. So here, where is my function divergent? Is there a place where my function integrand diverges? Well, it diverges at x close to 0. The integral is range is infinite. So let me just separate.
So can you give an example of the previous thing you said? A finite valued function with infinite area under the curve.
The integral is finite everywhere. It goes to 0 at infinity, but the integral diverges. So let me write this integral Okay, so I know that I might have a problem around x is equal to 0. I know that I might have a problem since the integration range is infinite. So let me write it in this form. From 0 to some epsilon. Well, here the range of integration is finite, but it is concentrated close to 0. So this might diverge because the integrand diverges close to 0. Here in the first integrand, epsilon was kind of an arbitrary small number. Here now I'm taking lambda to be an arbitrary but a very large number. But if you look at this integral, integrand is finite everywhere within that range, and my integration range is finite, so that integral is definitely finite. This integral, the integral is finite everywhere, but the range is infinite, so it might still diverge. Well, let's start with the last one. You see, lambda is very huge. So x is a very huge number within this integral. Finite, but a very huge number. But in that case, e to the power x is much larger than 1, so I can just ignore 1. And this is definitely convergent. You see, if you like, you can write this as from 0 to infinity minus 0 to lambda. The second integral is, integrand is finite, range is finite, so it's finite. The first integral is the famous gamma function. Gamma 3 over 2 is a finite number. So this term is finite. This term itself is also finite. The only possible source of divergence is the first term. Left is the first term. So let's look at the first term. Epsilon is very small, very close to 0. So I can use Taylor expansion to expand e to the power x. So then approximate value of this integral is just the integral of 1 over x to the power 1/2. So here we see that the integrand diverges. I'm basically writing an approximate expression for the original integral. But if it's a good approximation, wherever my original integrand diverges, my approximation should also diverge. But that integral is trivial to evaluate. This is x to the power 1/2 divided by 1/2 x ranging from 0 to epsilon, which is finite. So you see that I divided my original integral to 3 parts. One of them was definitely finite. The other 2, they could potentially diverge, but in this particular case, it is finite. So everything is finite. My integral is finite. So I have a finite TC, the critical temperature. At this critical temperature, my N0 is 0. This is 0. N lambda C at critical temperature, N lambda cube minus zeta 3 over 2 is 0. But as I lower the temperature, lambda becomes larger and larger. So N lambda cube becomes larger and larger. And hence, N0 just becomes finite. Let me write it in a slightly different form. There's N0, which is the number of condensates divided by volume. this is equal to n let me write it slightly differently. N lambda cubed divided by n lambda c cubed times n lambda c cubed. I basically would like to get rid of some coefficients. Minus zeta 3 over 2, but this is zeta 3 over 2. That is the definition of the critical temperature or the critical wavelength. You see, I have this equation over here. In that ratio, I would get T critical over T to the power 3 halves. Or NON 0 over V So this is how the number of particles in the ground state in Bose-Einstein condensation changes. You see, at T is equal to Tc, it is 0. As T becomes smaller than Tc, it becomes larger and larger. Eventually, of course, it can at most be N. If this is the critical temperature, above the critical temperature it is 0 or negligible. Below the critical temperature, it increases. Now we see, if you look at over here, the derivative of n0 as a function of t for large temperatures larger than Tc, that is 0. But the moment it becomes below Tc, it's non-zero. Well, this is in the thermodynamic limit. That is the first thing we should keep in mind. Only in the thermodynamic limit we have that discontinuous derivative. So n is continuous, but its derivative is not continuous in this transition, in this condensation. For a finite system, the derivative will change very fast, but still it will be continuous. Did I make a mistake somewhere? See, what I expect is n0 over n to be 1 minus, oh no, okay. No, there's no mistake, sorry. Now, if you convert this to n0 over n, what you should get is 1 minus t over tc to the power 3 halves. If you convert the other stuff. If you convert instead of v, if you use n, this is what you should get. And you see that at t is in this expression, at least when t is equal to tc, when t is equal to 0 and 0 is equal to n, it's more clear. When t is equal to tc and 0 is 0. Now, this is the number of particles in the condensates. Well, we have other properties, like what about the pressure? Yes, we had already seen one phase transition. Here I'm calling this a phase transition, but I didn't yet show that it is actually a phase transition. There is one hint over here. You see what happens during a phase transition is certain quantities change discontinuously. That's the characteristic of the phase transition. For example, if you have water, the volume per particle of liquid water and the volume per particle of water vapor, they are different. So there is this phase transition of evaporation where this quantity changes discontinuously. Here, the number of particles in the ground state doesn't change discontinuously, it changes continuously, but its derivative changes discontinuously. And again, if you remember our discussions of the evaporation, we had seen that the pressure only depended on the temperature, it didn't depend on the volume. So do we have such a thing over here? How does the pressure changes for the system below this critical temperature? So that is what we will study. What about the energy? What about the specific heat? But those things we will do, let's give a break here. We will continue in the second half. Now, any questions up to here?
This definition of phase transitions is Landau's definition. We're just not calling it that.
What is the Landau's definition that you are mentioning?
There's an order parameter that varies discontinuously across the transition. It's the same thing, but there's no.
I see here in this phase transition, the order parameter is usually the number of particles in the ground state. It doesn't change discontinuously. It changes continuously. But still, we call it a phase transition. In fact, we call it a second order phase transition because not the order parameter itself changes continuously, but its derivatives are changing discontinuously.
Lastly, what did you say we're going to compute in the second hour? Energy, pressure?
The pressure, energy,
that's it? Oh.
yeah. What else would you like to study? And in fact, we will also look at the specific heat. The heat capacity, and what about the derivative of heat capacity as a function of temperature? Is it continuous?
Quick question, sorry. In this N0 over N formula, do we have something additional? I mean, when T is greater than Tc, it seems like it's incapable of.
No, this is
giving
for
us-
T less than or equal to Tc. And 0 over N is 0 for T larger than Tc.
On the plot you just now, is the curve underneath TC, so lower than, for temperatures lower than TC?
Mhm.
Is that a circular or logarithmic?
Well, you see, this is the function, neither circular nor logarithmic.
Ah, okay. I got it.
So see you in the next hour.